Every year, tens of thousands of Virgin Media's 6 million customers lose internet because the cable providing internet to their house develops a fault, further deteriorates, and finally breaks. Not only is this incredibly frustrating for the customers, as they're left without internet for potentially weeks while they wait for engineers to diagnose their issue and change their cable, but also incredibly costly for Virgin Media, as they spend multi-millions of pounds yearly in reactive network maintenance. Good afternoon, I'm Arman Aryaeipour, and today I'll be talking about my project in proactive network maintenance with Virgin Media O2. In the UK, internet is provided to the vast majority of houses via underground cables from an internet service provider's data station. However, the underground world is quite a harsh environment as cables slowly deteriorate, develop faults, and finally break. So what does this mean for customers? Well, when a customer's cable modem sends a sharp signal through an intact cable, it arrives at the data station as a sharp signal. However, when a customer's cable modem sends a sharp signal through a faulty cable, then the signal distorts over the fault and arrives at the data station as a noisy signal, decreasing the upload and download speeds of the customer and decreasing their service quality. Luckily, modern cable modems are extremely smart and know exactly how to pre-distort a signal so that once it passes over a fault, all that is left is a sharp signal that arrives at a data station. Hence, a cable fault can develop, however, the customer will not notice as the service quality stays the same. But this is only a short-term solution, as a faulty cable will inevitably deteriorate and break. Therefore, the challenge is to find faulty cables before they do and a customer loses internet. The question of my project was, using machine learning, can we predict which customers have faulty cables by analyzing their pre-distorted signal before they lose internet? To carry out my project, I created a pre-processing pipeline that queried the raw cable modem data of Virgin Media's 6 million customers and computed the pre-distorted signal of each cable modem, as this is the only data that was available on the customers. Then, using mathematical transformations such as Fourier transforms, I recovered the original distortion signal caused by a fault, which I used to calculate various signal metrics, like the signal strength, to use as features in a machine learning tool, and very importantly, approximate the distance to a cable fault, so that an engineer knows exactly where to dig up for a customer. Initially, I tackled this project with an unsupervised learning technique, as no labels existed in the dataset to show whether a customer had an intact cable or a faulty cable that was deteriorating. Therefore, I used the clustering tool HDBScan and the 40 metrics I computed to isolate faulty cables from intact cables. However, it was at this point in the project that talking to the right people really paid off and networking paid off, because talking to other teams at Virgin Media made me realize historical data sets exist on faulty cables, so therefore I could map that historical data set to my data set and create a ground truth set of customers with faulty cables and intact cables. So that's exactly what I did, which allowed me to calculate the precision score of the clustering algorithm to know how well the clustering isolates faulty cables from intact cables. However, the clustering algorithm could not isolate any more than 10% of the faulty cables in any one cluster, which means that it is not good at distinguishing faults from intact cables. Now, at this point, you may be thinking, well, if you have a ground truth dataset, why don't you apply a supervised learning approach to this, a smarter way? So that's exactly what I did, and trained a random forest classification model on the metrics to find faulty cables and intact cables and distinguish them. This model trains very well, as you can see. However, when we test the model on new data, it is not able to distinguish faulty cables and intact cables at all, meaning that it vastly overtrained on the metrics that we gave it. Now, you may be thinking this project only had negative results, but I disagree, because what we did was eliminate analysis strategies and really learn from the project. So we learned that the metrics we employed were not good at distinguishing cables that were faulty and intact. This is because the faulty and intact cables have distributional characteristics which are very similar. So therefore, going forward, we know that we need to prioritize the signal spectrum in order to find better metrics to train our models with. But we have also found out that the metrics we employed are really fantastic for pre-filtering the data sets, even before applying any machine learning tools to them. We've also learned that by time averaging customer data over hours or days, we can better assess if a customer has a cable fault or not, instead of using a static time model like I did. So many, many ways to go forward and many lessons learned. Thank you very much.